So we saw two types of slopes. One was a infinite slope, as you can see on the bottom figure, and the other one is a finite slope, which is having a boundary on the base and top of the slope. So basically, the infinite slope failures, we call them translational slip, and finite we call them circular or rotational slip. Okay, just for your information. Okay, because you can see in the case of infinite slopes, basically the slip surface is going to be parallel to the ground surface, and in the case of finite slope it's going to be circular. All right, so these failures are called rotational failures or rotational slips, and these ones are called translational failure or translational slips. Okay, so stability of infinite slopes or translational failures, we saw yesterday this figure, and we derived the expression for factor of safety in terms of shear stresses, right? You remember this derivation? Okay, so we saw the basic concept yesterday. We saw that we found out the weight of the wedge. We found out the driving forces here. We found out the normal stresses here. We resolved the reacting stresses, normal stress and shear stresses we calculated. And in terms of the shear strength of the soil and the shear stresses due to the slope, we found out the factor of safety against failure. This we saw yesterday, right? So today we will see separately, we will see the factor of safety equations for cohesionless soils, C5 soils, and C soils. Okay, purely cohesive soils. Right. So if you look at the strength envelope, Mohr Coulomb strength envelope. This is our tau sigma space. As you can see here, we saw so many tau sigma spaces in the Mohr Coulomb criteria, Mohr theory, Mohr Coulomb theory. When we draw the Mohr circles, etc. So you are very familiar with sigma tau spaces, and this is a sigma tau space, and the line OA, the line OA here represents my Mohr Coulomb strength envelope or failure envelope. All right, I am pretty sure everyone are 100% confident with what this Mohr Coulomb failure envelope or strength envelope is. It's our failure envelope. All right, so it represents a system of stresses, a system of sigmas and taus, the maximum sigmas and taus, the sigma and tau combinations the soil can bear, right? That is my strength envelope, Mohr Coulomb strength envelope, OA. Okay, so that is inclined at an angle phi. This is purely cohesionless soil, so there is no C intercept, and the strength envelope is inclined at an angle phi. Okay, as you can see in this figure. All right, so C is equal to 0 in this case, and tau F is nothing but sigma tan phi, isn't it? My tau at failure is a combination of, it's a function of sigma and this phi. So it's basically the equation of this line, tau is equal to sigma tan phi. All right, that is my shear strength of the soil. Right, basic shear strength equation is tau F is equal to C plus sigma tan phi. So C is 0 here. So basically my equation is tau F is equal to sigma tan phi, which is represented by this line, the Mohr Coulomb strength envelope, OA. Right, so if the slope is inclined at an angle I, all right, you can see it is represented by line OB. So a slope inclined at an angle I, this line OB represents a system of stresses on that soil, of a soil element in that slope, which is inclined at an angle I. So that also have a system of stresses, a combination of sigma and tau in various points like this. Right. So consider a stable slope, consider a slope inclined at an angle I, which has a system of stresses represented by sigma and tau along this line OB. Okay. Now by sigma by T, we derived the expressions for sigma and tau in terms of sigma z yesterday, right? Sigma z was the normal stress acting on the critical failure surface, isn't it? So sigma c cosine by sigma c sin I is my sigma by tau. So cancelling the sigma z's, I have cosine by sin I, which is equal to cot I, which is a constant, right? So for a slope of inclination I, basically my sigma and tau varies, but that relation is constant. It is cot I, isn't it? You don't have to derive it even like this, because we know the basic equation, tau is equal to sigma tan phi, right? Right. So I know that if that phi is I, so I know that tau is equal to sigma tan phi. So sigma by tau is equal to cot I or cot phi. If it is phi, it is cot phi, isn't it? So that is always going to be a constant, isn't it? So same thing I am representing here. So by sigma by tau is equal to quantile, which is a constant. So I can say that the relationship between sigma and tau is always going to be a constant, right? It's along this line, right? Just like my sigma and tau equation for a slope inclined at an angle phi, right? Tau is equal to sigma tan phi. So tau by sigma is equal to tan phi, sigma by tau is equal to cot phi. Similarly, for this line I, for this line OB inclined at an angle I, the relation is same. Any combination of sigma and tau along this line OB, it is a constant, cotile, right? So for OB inclined at an angle I, my sigma is equal to tau cotile. From this equation I get my sigma is equal to tau cotile and tau is equal to sigma tan I, right? We know that relation, right? Tau is equal to sigma tan I know that, right? So when this I is equal to phi, when this I approaches phi, that means the slope angle reaches the maximum angle of internal friction of that soil when I is equal to phi, right? In that condition, my tau on that line will be equal to the tau f, correct? So it will reach the maximum sigma and tau combinations that soil can withstand, right? So if my I can say that if my I is less than phi, my slope is going to be stable always, because that for that slope inclined at an angle I, the combination of stresses sigma and tau will always be less than the combination of sigma and tau along the more Coulomb strength envelope, right? So I can say that a slope inclined at an angle I will always be stable, because the system of stresses will always be less than tau f and sigma f, right? Which will be along OA. So when this I approaches tau, then my tau will approach tau f, isn't it? The tau along this line will approach tau f when my I approaches phi, right? So my factor of safety equation, basic factor of safety equation, what we saw yesterday, it is equal to tau f by tau, which is resisting moments by driving moments, or resisting forces by driving forces, right? So basically it is tau f by tau, correct? So this tau f along this line MC strength envelope OA, I have my tau f, which is nothing but sigma tan phi, right? Tau f is equal to sigma tan phi. We know that equation, right? And tau along that line will be sigma tan I, correct? When I is equal to phi, correct? So tau will be equal to sigma tan I. Tau is equal to sigma tan I. So basically my factor of safety equation will become equal to tan phi by tan I, isn't it? So a factor of safety of 1 means my tan I is equal to tan phi, which is I is equal to phi basically. And for any I less than phi, my shearing resistance is not fully mobilized and my slope will be always stable. But if my I is greater than phi, which is represented by the line OC, can there be a stable condition there? No, right? Because my tau will be greater than the tau f, or the failure shear strength, or failure shear stress of the soil, or the shear strength of the soil is tau f. But along the line OC, which is an unstable slope, you can see that the tau values are all above the MC strength envelope. So it's a unstable slope, isn't it? So if your SLI is increasing above phi value, then obviously your slope is going to fail, right? The more circle will be above, outside that more Coulomb strength envelope. So obviously it is a unstable condition. We know that, isn't it? So when your I is less than phi, you have a stable slope. When I is equal to phi, that is equal to factor of safety is equal to 1, you can say that it is an equilibrium condition. But when your factor of safety decreases below 1, that is your I value is above phi value, then your factor of safety is equal to tan phi by tan I. It will go below 1 and your slope will be unstable. Clear? This is the condition of cohesionless soils. Is it clear? I hope it is clear. If you are considering cohesive friction soils or C5 soils, right? C5 soil, basically what you see in the site will most probably be a C5 soil, which is a combination of C and phi. So you look at this figure, don't look at the whole figure at once. Okay, look at this figure step by step as I explain. Let us explain and go ahead. Okay, so imagine the same tau sigma space. So this is the C5 soil. So obviously OD is my cohesion, right? We saw the more circles and shear strength envelope for C5 soils. We have seen that. So you know that there will be a C intercept along this tau axis. So you can see that there is a C, and the line will be inclined at an angle phi. We know this, right? So basically my shear strength of the soil tau f is equal to C plus sigma tan phi, right? That's my basic equation, isn't it? Now if your I, you can see here, the slope is inclined at an angle I. This line represents the system of these two lines, OB and F. Okay, the line DA represents my more Coulomb strength envelope. Line OB and line OF represents different slopes inclined at angles I. Okay, you can see here. So let us look at line OB now. Okay, this is line OB. This represents a system of stresses where my I is less than or equal to 5. Okay, this pretty much it looks parallel. So let me say that this I is equal to 5. Okay, line OB represents I is equal to 5. Okay, and this line OF represents a system of stresses where the slope is inclined more than the value 5. So you can see that the slope is still stable up to a particular depth, and which is marked by the point F. At the point F, my tau meets tau F, isn't it? So up to a particular depth, the slope can still be safe, isn't it? Even if your I is greater than 5, correct? Why? Because the soil is a C5 soil and there is some cohesion to hold the slope in place, isn't it? Phi is not the only strength providing parameter for that soil, because it's also having a cohesion parameter, isn't it? Now let us look at these equations. So if your I is less than or equal to 5, that is my line OB, system of stresses on line OB. When your I is less than or equal to 5, then the system of stresses, the shear stresses on this line, that is my tau, is always less than my tau F, which is represented by dA, isn't it? dA represents tau F, and you can see that the tau on line OB, it is always less than tau F, right? That happens when my I is less than or equal to 5. Even when my I is equal to 5, then tau is not equal to tau F, right? Even when my I is less than or equal to 5, still always my tau is less than tau F, as you can see from this figure, correct? Is that clear? But if my I is greater than 5, I is greater than 5 represented by line OF, you can see here I is greater than 5. At some points your tau is less than tau F, but you can see that there will be a point where your tau is greater than or equal to tau F, right? You can see at this point your tau is equal to tau F, and above that your tau is greater than tau F, right? So after this, up to a particular depth, you can say up to a particular depth, the slope can stand on its own. But as the depth of the slope increases, the system of stresses increases, your shear stresses developed increases, and the steeper the curve or the deeper the curve, your tau can be equal to tau F, and after a particular slope or after a particular depth, your tau can be greater than tau F and the slope will be unstable and it can fail. So at this point, your tau is equal to tau F and the slope is just stable. So what you have to understand from this figure is that your I, the slope angle, can be greater than 5 and the slope can still be stable up to a particular depth, which I call the critical depth, ZC. Okay, so up to a particular depth, my I can be still greater than angle of internal friction of the soil, but as the depth of the slope increases, your shear stresses induced can also increase, and at one particular point your stress combinations can be sigma and tau F, which will be at a depth ZC, which is my critical depth, where the slope is in equilibrium, and any depth further, you dig any further with an unsupported excavation, your slope is going to fail. Now I want you to visualize this. Okay, I want you to visualize this. Visualize the previous case as well. Imagine a soil slope. Okay, it is a purely sandy soil. Imagine a soil slope. Okay, just imagine, dropping a heap of sand. Okay, that slope angle can never be greater than the angle of internal friction of the soil, isn't it? So if it is steeper than that, it cannot stand on its own, so the soil is going to slide down, right? Cautionless soil, purely cautionless soil. But if you mix some clay soil with that, all right, even if the slope angle is 30 degrees, let me say the phi of the soil is 30 degrees. If the slope angle is, it will definitely stay at the slope angle, if you make a heap of the heap with a soil like this C5 soil, and you make the slope angle 30 degrees, suppose the phi of that soil is 30 degrees, you can easily make that slope last, isn't it? Even maybe you can even make a slope up to 40 degrees or 45 degrees because the soil is having some cohesion and it can stand on its own. But if you increase the depth of that slope, you keep on pouring more soil. At one particular point, that slope is going to fail, isn't it? Because the stresses induced will be greater than it can bear. Even when your I is greater than phi, it will reach such a point where your sigma and tau is equal to sigma is f and tau f. That is, it will reach failure at that critical depth. If you keep on increasing the depth of that slope, at one particular point, your system of stresses will be equal to the failure stresses, and the whole slope can slide down. Right? I want you to visualize that. Could you do that? So greater the I, smaller the ZC. What does that mean? So if you keep on making your slope steeper and steeper, the height up to which you can build a slope like that or a stable slope like that will be lesser, isn't it? Because always a flatter slope is safer, right? Obviously a flatter slope is safer. So, and you can go for larger depths, right? You can go for larger depth of slopes. But if your slope is steeper, greater the I, then obviously the critical depth is going to be lesser, isn't it? So greater the I, smaller the ZC, correct? So even if I is greater than phi, unlike sandy soil, the slope will be stable up to a particular depth. That depth I call it ZC, at which your sigma and tau will be equal to sigma f and tau f, where it will be just stable, right? So you increase the depth of the slope a little bit more, then your slope is going to fail because the system of stresses are going to be higher than the stresses on the Mohr Coulomb failure envelope, isn't it? Right? Let's derive that. So at depth Z is equal to ZC, I told you when the depth of the slope reaches the critical depth Z is equal to ZC, at that point your shear stresses induced in that soil will be equal to the shear strength of the soil, right? So factor of safety at any depth below C1, as you can see in this figure, any depth below C1, any depth below this, throughout these points, as you can see here, any depth below C1, any depth below C1, that is system of stresses here, where the I is greater than phi. So along this line, the system of stresses along this line below depth C1. Okay. So system of stresses along this line. So in that cases, my F is equal to tau F by tau, where tau F is nothing but C plus sigma tan phi. I know the equation for tau F, divided by tau, divided by the stresses along shear stresses along this line, right? And from the derivation yesterday, we saw that sigma is equal to gamma c cos square I and tau is equal to gamma c cos I into sin I. We derived these two equations in terms of sigma z. Do you remember this one? We saw this day before yesterday, right? Sigma is equal to gamma z cos square I and tau is equal to gamma c cos I sin I. We derived this yesterday. So from that, I have sigma is equal to gamma z cos square I and tau is equal to gamma c cos I sin I. Then I'm going to substitute these values here. All right. So my factor of safety F is equal to C plus sigma is gamma z cos square I into tan phi divided by, I want you to derive this with me. Take this down, divided by tau, and tau is equal to gamma c cos I sin I, right? I know this. Correct? And at that critical depth, Z is equal to ZC and tau is equal to tau F. When factor of safety is equal to 1, when this factor of safety is equal to 1, that means at this point, at the point F, where my factor of safety is equal to 1, that is my tau is equal to tau F, substitute 1 here so that this will be equal to this, right? So C plus gamma ZC cos square I tan phi, it will be equal to gamma into ZC cos I sin I, right? So rewriting it in terms of this critical depth, ZC is equal to C by gamma tan I minus tan phi into cos square I. Now again rewriting it in terms of C by gamma ZC, C by gamma ZC, I'm going to take this part above. So it will be equal to tan I minus tan phi into cos square I. Correct? Derive with me. Please derive with me. So you will get the gist of it. So this particular constant, this is the constant you can see, right? This is the constant, isn't it? C, cohesion of the soil, gamma, density of unit weight of the soil, and Cc, critical depth of that soil. These three parameters are constant, isn't it? So these parameters, the ratio of these parameters is called Sn, or stability number, which is a dimensionless parameter. Okay, so this C by gamma Zc stability number will be here. It will be equal to tan I minus tan phi into cos square I, which is a function of angle of internal friction of the soil and the slope angle. So that represents my stability number. So we will use this later when we do problems. Okay. Right. So this Sn is my stability number, which is a ratio between C and unit weight and critical depth of the soil. Right. Now I can also write the factor of safety in terms of cohesion. That equation will show Fc is equal to C by Cm. Fc represents factor of safety with respect to cohesion, which will be equal to C by Cm. Here you can see this relation is similar to this tau f by tau, where tau f represents the maximum shear strength of the soil. This C represents the maximum cohesion of the soil, and tau represents the shear stresses in the soil. Here Cm represents the cohesion mobilized in the soil. So factor of safety with respect to cohesion also you can represent. So here it will be Fc is equal to C by Cm, but it is not the true factor of safety. It is a factor of safety with respect to cohesion alone. Okay. So now stability number Sn is equal to, we know the equation, it is C by gamma into Cc. I want you to derive this again with me. So C by gamma into Cc I know. So when it is in equilibrium, it will be equal to Cm by gamma into Z, right? Correct? When it is in equilibrium, the C will be equal to Cm. That is, the mobilized cohesion in the soil will be equal to the maximum cohesion. Maximum cohesion of the soil will be mobilized when it is in equilibrium, and the depth of the depth will be Z, right? So C by gamma into Zc is equal to Cm by gamma into C, which will again be equal to, I can rewrite this Cm in terms of Fc by C, right? Sorry, Cm will be equal to C by Fc, correct? So I'm substituting that here. So C by Fc into gamma C. So write this, and you can cancel those terms, and you can write that the factor of safety with respect to depth. So factor of safety in terms of cohesion, I can also write it in terms of depth. So Fc will be equal to Zc by Z, right? So you can cancel these terms here. You can cancel the C and sigma here, and you can also cancel the C and sigma here. So your equation will be equal to 1 by Zc will be equal to 1 by Fc into Z. So Fc will be equal to Zc by Z. So you can also write the factor of safety in terms of depth. You can also represent your factor of safety in terms of cohesion. Okay. If you are considering purely cohesive soil, we know how the Mohr circle envelope is going to look, because purely cohesive soil means the phi is 0, there is no sand content, there is no angle of internal friction, the strength is basically from cohesion alone, right? Tau f is equal to C. So the Mohr Coulomb envelope, how will it look? That is tau sigma space. You can see that you have the C intercept, and there is no inclination of this line because there is no phi. So it will be constant, right? System of stresses will be constant. So whatever normal stress you apply, your tau f is going to be constant. We saw this in shear strength concepts, right? So your Mohr Coulomb strength envelope will be parallel to this. So you can see this tau is equal to tau f is equal to C. Tau, whatever be the sigma, your tau f is going to be constant, and that will be equal to cohesion of the soil. We saw this. All right. So for any depth below f, this is my point F. All right, and this line OF represents my slope, the system of stresses along the slope, which is inclined at an angle I. So any depth below F, that point F represents the system of stresses sigma and tau F. Okay, sigma and tau F. So any depth below F represents the stresses less than that. So for any depth below that, whatever be the point, I know that my tau f will be equal to C, and up to a depth Zc, that is up to this system of stresses, my slope is going to be stable. All right, and at the depth Zc, or the critical depth at this point, my tau will be equal to tau f, right? My tau will be equal to tau f, and my factor of safety will be equal to 1 because it is just at equilibrium. So factor of safety basic equation, tau f by tau. So here tau f is nothing but C, and tau, we saw this relation earlier, tau will be equal to gamma into Zc into cosine. sin I, cosine into sin I. Tau f by c, tau f by tau, c by gamma into gc into cosine into sin I. So then if you rewrite it in terms of gc, so it will be equal to c by gamma into cosine into sin I. So again, writing it in terms of my stability number, c by gamma into gc is my stability number. So writing it in terms of that, I can see that it is a function of angle of the slope alone. There is no angle of internal friction parameter. So here stability number will be equal to cosine into sin I, and again I can rewrite my factor of safety in terms of cohesion. So F is equal to Gc by C. Clear? This is very simple. All right. So I gave you the equations for factor of safety for the basic factor of safety in terms of tau f by tau. Then for cohesionless soil, tan phi by tan I. For cohesive frictional soil, C plus sigma tan phi by tau, and in terms of this I derived it and I came to the representations for factor safeties with respect to cohesion. I derived my stability number and I also represented my factor safety in terms of depth of the slope. And in the case of purely cohesive soil, my F is equal to C by gamma Gc cosine sin I, and again I represented my stability number cosine sin I, and I also represented factor safety in terms of depth. Here Fc is equal to F, isn't it? Because there is only C, there is no phi. So Fc is equal to F, correct? Factor of safety in terms of cohesion is the same as factor of safety because there is only cohesion here, right? Is that clear? Hope it's clear. Then stability of finite slopes, which is also called a rotational slope or rotational failure. We saw that the slope critical failure surface or critical surface of failure is going to be circular, or it's a arc of a circle or a arc of a log spiral, as you can see here, right? Different types of failure of a finite slope. A finite slope is a slope which has its boundaries set, right? You have a finite base and you have a finite top, right? So here you can see this critical failure surface here, a finite slope here you can see, and you can also visualize your critical surface of failure here, right? So in the case of finite slopes, the failure surface is considered to be a curve rather than as a plane, which we saw so far in the case of infinite slopes, right? Different types of failure you can see. You can fail along the face of the slope, you can fail along the toe of the slope, and you can also fail covering the base of the slope, right? Different ways it can fail. So it is basically classified into two types of slope failure, two types of finite slope failure. One is a slope failure and other one is a base failure. Okay, so in slope failure we have two types. One is a face failure and toe failure. So slope failure, this is the slope surface, isn't it? This is my slope surface. As you can see my mouse moving, this is my slope surface. So a failure along a surface or sliding or slippage that intersects the slope at or above the toe. This is the toe of the slope and this is the top of the slope, this is the base of the slope. Okay, so if your failure is along a surface of sliding or slippage that intersects the slope at or above the toe, that means your failure surface, like this, your failure surface intersects the slope at or above the toe. As you can see here, at the toe, the critical failure surface is intersecting at the toe or above the toe, as you can see here. All right, so if it intersects above the toe, you call it a face failure. That means failure occurs along the face of the slope, as you can see here, the second image. You can see here this failure occurs along the face of the slope, and if it intersects, the failure surface intersects the toe, you can say that the failure occurs at the toe, and you call that failure a toe failure. Again, it happens along the face of the slope, and you can call this a toe failure. Okay, so face failure and toe failure. So face failure is nothing but the failure surface is above the toe, and this happens generally when the slope is high and the soil is weak on the top and strong at the toe. If the soil is weak at the top and strong at the toe, then you can expect a face failure. All right, and when the slope is steep and the soil is relatively homogeneous, you can expect a toe failure like this. All right, clear? So when the soil is weak on the above the toe and strong at the toe, then you can expect a face failure. When the soil is pretty much homogeneous and the slope is steep, you can expect a toe failure. So these two are called slope failures, where the failure surface intersects on the face of the slope at or above the toe. Okay. Then I have a base failure. So this happens when the soil beneath the toe is weak. The soil here, if it is weak, then the failure occurs along a surface that passes some distance below the toe of the slope. As you can see, the failure surface doesn't intersect on the face or doesn't intersect on the toe. This passes through some depth below the toe and intersects at some point after the toe, as you can see here. So this basically happens when the soil beneath the toe, the soil here is weak. Okay, if the soil here is weak, then your failure surface can pass through the toe and the complete base of the slope can fail. So this is called base failure. Clear? So we will wind up for today.